Hi, hello, yeah. We'll continue our series on machine learning using R, and today I want to talk about fit a longitudinal random forest using a package called a LongituRF. So basically, we're trying to build a random forest for longitudinal data, uh, like repeated measures over time, or you get multi-level data structure. So longitudinal random forest models handles repeat measures, capturing within subject correlations and time-dependent patterns. And the longitude RF package in R fits random forest to longitude data using fixed and random effects and subject IDs and time point. Okay. It supports flexible stochastic processes such as Brownian motion to model serial correlations over time. And outputs include predictions, random effects, variance estimates, and log likelihood evolution. And LongRF is best for prediction and variable importance, and not formal statistical inference or hypothesis testing. So it's a prediction model, not explanatory model. Okay. All right. First, we need to install it. So I already did. So I just load it in. And set a random seed. And now I need to create a data set. In this package, there is a function called the data long generator. So I'm calling that function to simulate n is the number of individuals, p is the number of predictors, and g is the number of predictors with temporal behavior. So here is generated. And I want to make a note here. This function is not robust. I found out that g must either be set to 0 or must be the same value as p. So in this case, g equal to 6. So basically, we're saying we have 6 predictors that changes over time. Okay. If you have another other value, like if you specify g equal to 3, this function will not run. Okay, so that's a note here. And then this data underscore long is not like a data frame, it's a list. Okay, so if you use structure, take a look at this data object, it's a list of 5. Okay. Then we'll fit a longitudinal random forest, and the main function is REEM forest, and the syntax looks like this: REEM forest. Parentheses, you're taking to x equal to data underscore long at x. So this is the data matrix for the predictors. Y equal to data underscore long at y. This is the data for the dependent variable, and z with the data underscore long at z. This is the random effects. And you get the ID and you get the time. And then you have stochastic, STO equal to BM quotes. So it has 3 options: BM, OU, or FBM. So BM is Brownian motion, OU is Ornstein, Uhlenbeck processes. FBM is fractional Brownian motion. So these are like longitudinal data with specification. And then M try equal to 2. We're going to try number of variables that is split. And N tree equal to 500. We use 500 trees. So a little more notes here. BM is also called the winner process. For modeling continuous correlated data over time. And OU is good for modeling mean reverting behavior, in which you see like data tends to revert to the baseline value. Okay. And FBM is good for more flexible long-range dependencies in the data. So here, the tools we have to model the correlation structure in the longitudinal data are very different from what we see usually in like GE models or linear mixed facts models. So remember in those models, we have like autoregressive, we have compound symmetry, we have other types of correlation structures. But here in this longitudinal random forest model, we have to use stochastic processes. Okay. All right. So we have fitted that. We need to fit that model here. Let's do this. That's going to run a little bit. Okay. Now the model has been fit. It R told us stopped after 7 iterations. So we can look into the structure of this object REM underscore fit, and you can see it's quite it's a list of 12, so there's a lot of information in there. Okay. So we're going to only use some of them to demonstrate what this package can do here. So first, just underline random forest object. So for example, we can extract information about the forest. It's just the usual information we usually read from random forest. So it tells us the regression, so dependent variable is continuous, a number of trees, 500. Variables tried at each split is 2. We get the mean squared residual, so we get the percent variance explained. It's 98.32, so that's a very, very good model. So we can also predict random effects per individual. We can fit that. And yeah, you can see it just print out this random effects for all individuals. Get your table here. It has 2 random effects. Maybe you can interpret it as the random intercept, random slope, if the regional model is a linear model. Okay. And we can estimate stochastic process value called omega for trajectories. For example, we can just subtract it rem underscore fit at omega. So this again is much longer. This is the contribution of the BM process on the specific individual at a specific time point. Okay, so this is really, it has the whole number of rows as the original data set, so 500, I think. And also, this part is really the within serial correlation, not explained by the fixed and random effects. And if you look at the mathematical formula for the model, it's the omega term in that model. Okay. So, all right. And also, we can plot out the likelihood evolution across iterations. So we can use this command to plot it out, and we use rem underscore fit at v raise ambulance. So what this means is it's recording, it's the recorded log likelihood value at each iteration. So you can see the graph is on the right hand side. So it's going down, going up, and eventually about 5 iterations. Okay. And it's kind of stabilized. But here, so this graph is good for us to visualize the convergence of the iterations. But I must make a note here. The REM forest, it uses maximum likelihood or restrict maximum likelihood to estimate variance components. Okay, so only part of the model, but it uses a sample tree method, but not likelihood, maximum likelihood in the tree building process. So it doesn't use maximum likelihood for the entire model. So it's kind of a mix of both estimation methods. Okay, so that's kind of a note I want to make here. And you can also extract out of bag error for iterations. By doing that, it gives us 5 iterations here. Okay. And we can, again, this is a prediction model, so we can do a lot of predictions. First, in-sample prediction, we can just use the training data and we can compare, the for the first subject, the observed versus the predicted y hat. So they're pretty close to each other, so this is pretty good. We can also predict for new data. So if we generate another data set for 10 subjects using the function, then we can just use this predict rim fit and then x, z, id. These are for the new data, and we can get that. Okay, so this is the predicted value for the new subjects. And also we can predict into the future. So if we want to predict, say, times 7, 8, and 9, we have 1 to 6, right? So we can just formulate the new x, new z, and then we say just repeat the new ID, just the first subject, and we can use the predicted the future for timing to the new time. Okay, and this is the predicted new value for the subject 1 into 7, 8, and 9 visit. And also we can plot out observed versus predicted trajectories for each individual. It looks like this for the first, I think, 6, first 6, right? Yeah, individuals. Okay, so you can see it predicted pretty well. The predicted curve follows the original curve, observed curve pretty well. All right. I hope you like this video and learned a few more things about longitudinal random forest. Thank you for watching. And please like our video, click the notification bell, and subscribe to our learning channel. And also, I will post these R codes in the comments area for your review and practice. Thanks for watching.